Alright, now we have covered for the example of LMTD. Alright, now we take a look the correlation equation of heat transfer by convection by using the heat transfer by convection. So we have a deal with Nusselt number. Okay, Nusselt number is being represented by Nusselt number NU, and then we have the Reynolds number followed by Prandtl number, and this particular equation of Nusselt, Reynolds and Prandtl, they are being used in heat transfer by convection in tubing. Okay, remember that you need to calculate for the LMTD when the cooling water and hot water is entering and leaving the tubing. And then you need to know as well that the convection, the heat transfer by convection also occur in jacketed kettle, steam jacketed kettle, as well as coil in vessel. Okay, this one, for example, the vessel, it has the coil underneath that particular vessel. Alright, so the first one, we have the steam jacketed kettle, whereby this particular steam jacketed kettle, it is being using steam. Okay, this particular lower part, this one is steam. Steam is being used to heat up the cooking, to heat up the material that you want to cook. So, and at the same time, we have the cooling water in order to maintain the temperature of what will be the desired temperature that we want. And this particular process is known as indirect heat transfer because the heat is not being using directly to cook the material, but we are using the other substance that is steam to heat up the material during the cooking process. So for this particular steam jacketed kettle, this one is basically to produce a large mass of cooking material, and normally it is being used by the industry. For example, you want to make for beef stew, or to make soup and etc. So basically they are using steam jacketed kettle because the temperature can be monitored. Okay, they will have the digital display over here and the temperature for the steam and for this particular cooling water and the steam to heat up the process of the cooking process can be regulated. Okay, and then we have this braising pan. This braising pan basically is whereby it is being used to make again for beef stew or to braise the meat, and at the bottom part of this particular braising pan, it has the coil. Okay, and can you see this is the knob to control the temperature. So this particular coil, it will increase the temperature in order to cook the material. Alright, now let's take a look for the example of jacketed kettle. Okay, for example, estimate the steam requirement. Okay, estimate the steam requirement. So this is your task that you need to calculate. Alright, what you need to do is you need to calculate for the amp of steam. As you start to heat 50 kg of pea soup in a jacketed pan, if the initial temperature of the soup is 18 degrees Celsius, and the steam used is at 100 kilopascal gauge. The pan has a heating surface of 1 meter square, and the overall heat transfer coefficient, okay, overall heat transfer coefficient, you need to know certain terms belongs to which parameter. Okay, so this one is U. The overall heat transfer coefficient is assumed to be 300 joule per meter square second degree Celsius. Alright, so from this particular problem statement, we have the temperature of pea soup. The initial temperature is 18 degrees Celsius, but the final temperature, we do not know what is the final temperature of the soup. So you need to find the final temperature of the soup when it is been given the information that the pea soup is being using steam at the pressure of 100 kilopascal gauge. So these particular values, you need to use steam table in order for you to get the temperature, okay, to get the temperature as well as to get the value for the latent heat, okay, the lambda, latent heat. And basically this particular value you can find on your own because you have learned how to use the steam table. Alright, so from steam table, saturation temperature of steam at 100 kilopascal. Basically, this one you need to use attachment number 1. At 100 kilopascal, the temperature is 99.58 degrees Celsius. How to get this particular temperature is by using interpolation. Remember, in chapter 4, you have learned how to do interpolation. And then the latent heat at this particular temperature, at this particular pressure is 2258.1232 kilojoule per kilogram. Alright, so the first thing first, what you need to do is that you need to calculate for the value of Q. Okay, it has been given the value for U, it has been given to you the value of A, and then you manage to get the temperature of the initial temperature and the final temperature. So you need to use the equation of Q equals to UA delta T. How do you know which equation of Q that you need to use is whereby you need to refer back to the problem statement. What are the information that has been given to you? Alright, if the problem statement presented to you overall heat transfer coefficient, you cannot use the equation of Q equals to mCp delta T. Alright, this is wrong because you do not know what is the value for Cp. But it is given to you the value for U. So that's why you need to use equation UA delta T. The value for A has been given as well. Alright, so now to solve this particular value for Q, then the value of U has been given as 300 times by the surface area is 1 meter square times by the temperature difference between the final temperature minus by initial temperature of P soup, then you will be able to get the value for Q as 24,470.4 joule per second. Alright, and then for number 2 is whereby you need to solve the problem statement that has been presented to you. So what you need to do is you need to calculate for the mass flow rate of steam. Okay, so this one mass flow rate, basically we are talking about kilogram per second. Okay, steam required per second. So how are you going to calculate for the mass flow rate of the steam per second? What you need to do is you need to calculate for the Q divided by latent heat. Q divided by latent heat. Okay, why do you need to calculate Q over latent heat? This one is because you need to cancel out the unit. The unit coming from the Q, the unit coming from the latent heat. Alright, so for example, for Q we have the unit of joule per second. Right, and then you need to over by latent heat, the unit is kilojoule per kilogram. So kilojoule is represented by 10 to the power of 3, okay, joule per kilogram. So because this one is per, so what you need to do is when you want to move this up, you need to turn this one the other way around. So what is going to happen is that it becomes, I do it over here, alright, it becomes joule per second, you need to times by kilogram per 10 to the power of 3 joule. Alright, can you see? Okay, this one is the mathematics that you have learned during your high school. I believe your teachers has taught you why this particular changes of kilogram and joule happen when you bring it upward. Okay, so from here, the unit for joule and joule can be cancelled out and you are going to live with kilogram per second times by 10 to the power of 3 because this one is the kilojoule just now, right? So what happened here is that 24470.4 divided by 2258.1232 times by 10 to the power of 3. This one is because it is represented by kilojoule per kilogram. Okay, so you will have the value of 0.0108 kilogram per second. Okay, this is the unit that left. Right, when you answer this particular question by giving this answer, then it is already correct. But if let's say you want to convert this particular second to become hour, then it is allowed as well, but then basically you can just leave it as per second. Alright, now let's move on to the next example. Example of heat transfer by convection, and this one by using vessel. Just now is jacketed kettle. Okay, what would be the rate of heat loss from the cooking vessel of the previous example? This one is meant for previous example. If a draught meaning that a flow of air causing the air to move past the cooking vessel at a speed of 61 meter per minute. Okay, can you see this one? The speed of air is 61 meter per minute. So what you need to do, first thing is you need to convert to become meter per second instead of per minute. So what happened here is 61, you need to times by 1/60. Okay, so the answer, assume the vessel is equivalent to a flat plate, then you need to use the equation of Hc equals to 5.7 plus 3.9V. Okay, where do you get this particular equation? Basically, this particular equation will be given to you, but to make you further understand where does this particular equation coming from, it coming from the previous example that we have discussed previously, whereby this one is a flow of air over flat surfaces. So if let's say the draught, the velocity of air is less than 5 meter per second, then you need to use the first equation. If the velocity is greater than 5 meter per second but less than 30 meter per second, then you need to use second equation. Alright, so that's how this particular equation is present here. Okay. So how do you know that you need to use this particular equation? That's why you need to calculate this particular velocity of air. Turn it to become meter per second first, then you will know why this particular equation is being selected. Okay, so calculate for the value of Hc, because now you need to calculate for the value of Q, but you need to use the equation of HCA delta T. Okay, so the value for Hc by using this particular equation, 5.7 plus 3.9 times by this one, 61 over 60. This one is meant for this velocity of air, 61 meter per minute. This particular 60 is to change from meter to become second. Okay, to convert from meter to second. So you will get the value of 9.7 joule per meter square second degree Celsius. This one is the Hc. Okay, and then we move on to the area is 3.4 meter square and delta T is 32 degrees Celsius. Okay, this particular information is basically meant for this particular problem statement, but it should be given in the problem statement. So this particular value is been given to you. For example, if let's say the area of the cooking vessel, okay, the area for cooking vessel is 3.4 meter square, and delta T during the cooking process is 32 degrees Celsius. Alright, so what will be the value of Q? Then you need to use the equation of Q equals to HCA delta T, whereby the value of HC has been calculated here, 9.7 times by area is 3.4 times by delta T is 32 degrees Celsius. Then you will be able to get the value of Q as 1055 joule per second. Alright, now we move on for the radiation heat transfer. This one is another method of heat is being transferred by using radiation. So for radiation heat transfer, the first subtopic we have the black body radiation. Radiation heat transfer is the transfer of heat energy by electromagnetic radiation. For example, the use of microwave oven. Microwave oven is using electromagnetic radiation. Okay, radiation, it operates independently of the medium through which it occurs and depends upon relative temperature. Okay, this particular radiation heat transfer, the radiation, the factor that affects the radiation, it involves with the relative temperature, 1. Okay, and then the geometric arrangement. Geometric arrangement, for example, does it being stacked vertically or does it being stacked horizontally? Okay. This one vertical, this one horizontal. So the arrangement of the food material in order for the radiation to pass through is very important when you want to have optimum radiation heat transfer. Okay, how the material is being arranged. Alright, and then the third one is the surface structure of the material that are emitting or absorbing the heat. The surface structure, okay, for example, whether it is a rough surface or smooth surface. Okay, for rough surface, basically it requires more radiation in order to heat up the food product. Smooth surface, basically it requires low energy of radiation. Okay, the formula for radiant heat transfer is by using the Stephen-Boltzmann law, whereby Q equals to epsilon A sigma T to the power 4, whereby the T is the absolute temperature by using the unit of Kelvin. Then for sigma, this one is a Stephen-Boltzmann constant, whereby the value is 5.73 times by 10 to the power of negative 8 joule per meter square Kelvin to the power of negative 4. Okay, and then epsilon, this particular epsilon is the emissivity of the particular body, and the value of the epsilon is in between 0 until 1. Okay, this one is not 0 minus by 1, but 0 until 1. Okay, the value of epsilon is in between of this particular value. Okay, it varies with the temperature and the wavelength of the radiation emitted. Okay, at low and moderate temperature encountered in food processing, epsilon, the value of epsilon is almost 1, then you will have a dull black surface. For example, the burnt toast or the burnt food material, then you can expect that the value of epsilon is 1. If let's say the value of epsilon is 0.9, then the surface such as paper or painted metal or wood, and including most food, okay, if let's say the value of epsilon is 0.9, if the value of epsilon is 0.7 to 0.25, this one is meant for the rough and unpolished metal surfaces. Okay, rough metal surfaces. And if let's say the value of epsilon is less than 0.05, then it means this one is for polished metal surface. Okay, this one is meant for the smooth surface, whereby it requires less energy. Okay, a black body gives the maximum amount of emitted radiation possible at its particular temperature. Black body, this one is anything that absorb all the lights, okay, and this particular material is known as black body. Radiation between two bodies, the radiant energy transferred between two surfaces depend upon this one I have mentioned just now, the temperature, geometric arrangement, and the emissivities, okay, the epsilon. For two parallel surfaces whereby it face each other, the net heat transferred from hotter to cooler surface is been given by the equation of Q equals to AC sigma times by temperature difference of T1 to the power 4 minus by T2 to the power 4, where 1 over C is equals to 1 over epsilon 1 plus 1 over epsilon 2 minus by 1. Epsilon 1 is the emissivity of the surface at temperature T1, and epsilon 2 is the emissivity of the surface at temperature of T2. Alright, now we move on to radiation to a small body from its surrounding. In the case of relatively small body in surrounding that are having a uniform temperature, then the net exchange is given by the equation of Q equals to sigma A epsilon times by temperature difference to the power 4, where epsilon is the emissivity of the body, T1 is the absolute temperature of the body, and T2 is the absolute temperature of the surrounding. And this particular equation, this equation number 1, is covering for many practical purposes in process engineering. For example, the loaf in an oven, whereby it receives radiation from the walls around it. And then a meat carcasses radiating heat to the walls of a freezing chamber. Okay, and then the third one, we have the radiant heat transfer, whereby equation number 2, Q equals to H RA minus times by delta T, whereby HR is the radiation heat transfer coefficient, T1 is temperature of the body, whereby T2 is temperature of the surrounding. Okay, and this particular temperature, basically they are using the unit of Kelvin. Okay, unit of Kelvin for the temperature. So if we equalize equation 2 to equation 1, because both are meant for the Q, okay, Q and Q, then you will get the value for HR. This one, if let's say we need to calculate for the radiation heat transfer coefficient, so the value for HR equals to epsilon times by sigma times by temperature 1 plus temperature 2 times by temperature 1 plus temperature 2 to the power of 2. Okay, so this one is meant for the radiation of small body from its surrounding. Alright, so this is how the equation is being derived. And another equation that is noteworthy, worthy for you to know, is whereby when you want to calculate for the value of Q equals to HRA delta T, and it also can be represented by Q equals to 0.23 times by epsilon times by Tm per 100 to the power of 3 times by A delta T. Alright, so this one is meant for the radiation of heat transfer. Heat transfer by radiation. Okay, the third mechanism of heat transfer. Alright, so in the following slide, we have the example of the radiation to a heat loop. And this one is very simple because you have all the equation given to you, right? But then you need to know the value is meant for which part. Okay, calculate the net heat transfer by radiation, meaning you need to calculate for the HR to a loaf of bread in an oven at a uniform temperature of 177 degrees Celsius. If the emissivity of the surface of the loaf is 0.85, so the emissivity is epsilon, using the equation of Q equals to sigma A epsilon times by temperature difference to the power 4. Compare this result with that obtained by using equation of Q equals to 0.23 epsilon times by Tm over 100 to the power of 3 times by A delta T. The total surface area and temperature of the loaf are respectively is 0.0645 meters square and 100 degrees Celsius. Alright, so how are you going to solve this particular problem? So the first thing what you need to do is you need to convert the temperature from degrees Celsius. This one is degrees Celsius. You need to convert to Kelvin. Okay, T1 is 177 degrees Celsius. T2 is 100 degrees Celsius. So this one is T1, this one is T2. Alright, so calculate the value for Q by using the equation that has been given to you, because you need to compare the value of Q by using both equations. So the first equation, you get 68 times by joule per second. Okay, and then for the value for second Q, you will get at 67.4 joule per second. So even with quite a large temperature difference, both equations will give you a close approximation result, meaning that you will get almost similar result when you are being presented with any equation that you are using, but then they are having a difference in terms of the temperature difference. Okay, so this should cover for the whole chapter 6, and I hope you make your own, you will do and practice your own tutorial for chapter 6, and we are going to discuss for your tutorial in the next video. Okay, so I'll see you in next video for the following chapter.